try to. I will first present the results joined with Masato Zuji, and then maybe I will discuss some open problems that I think which I think will be interesting for this audience. But first let us start with the definition. But maybe the definition of Anosov flow. So I guess everyone knows. So I don't write it, right? Continuous splitting of the manifolds. Tangent space split into three invariant subspaces for the flow, and this denotes the central space and the flow direction. And then maybe some of the audience are not familiar with the transitivity. So when we say a map is transitive, so this is definition. So that is to say that there exists a dense orbit. Orbit. Okay, and then let me also talk about the so-called SRB measure, and I see that tomorrow there will be, and also the day after there will be people who talk about it. So to set up correctly the notion of SRB measure, maybe we need more definitions, but in this case, for transitive Anosov flow can be defined as the unique. So in this case, there exists a unique measure, which is the weak star limit. Push forward the volume from M infinity. But usually, for other flow, there's no reason such a limit exists. Also, another thing about this SRB measure is that, and this is also for Anosov flow, for general maps, there's a notion called a physical measure. But also in some cases people call it SRB measure, but it means still the same thing, meaning that we say given a map, let's say F, on some manifold, with the Vega measure defined. We say that a measure nu, F invariant measure, probability measure. We say that is a physical measure if you consider a set of points so that if you take the this empirical measure starting from X and along the orbit of X, and this will converge to nu. Right? So we say this is just a definition of the basin of the measure. We say a measure is a physical measure if the Vega measure of the basin is positive. So it means that, for instance, there's some cases you can have, say, periodic orbit, but in that case, it does not tell you anything about how other points move, right? And if some measure is a physical measure, it means that this measure describes the asymptotic behavior of a positive measure with respect to the positive Lebesgue measure set of points. So in this case, it is known that the unique as measure is a physical measure with a full basin. But in general, it is usually very hard to show the existence of a SLB measure. Maybe this is not why this is hard for the audience, but just believe me that this is very, very hard. For instance, there's for this so-called Hannon map. People can only prove in for a very small b and for some set of a, such a measure exists, and the proof is extremely complicated. And till now, it is not very well understood and how to get a reasonable proof for this. For other maps with less structures, it will be seems even harder. And even for perturbations of Anosov flow, for the say there are very few good results, very few general results for it. And what the Masato said is for this, in your case, you construct several physical measures, right? I did miss your talk.
Sorry, if it's setting?
In your talk,
yes,
you have several physical measures constructed by this case. Yeah, but for diffeomorphism, constructing this physical measure is usually harder, a lot harder than for animals. And also, let me present a more general class of invariant measures, but for transitive Anosov flows. So it is called the equilibrium measure. Defined in the following way. So once this G is defined, let us take a function, let's say f, and then we usually take this Hilbert function, and then it is known that there exists a unique measure invariant by G, such that this quantity, let me see, I think it's this quantity. This quantity is maximized by this mu equals to mu f. Okay, there's a unique maximizer, which is a invariant measure by f. Yeah, there's a conjecture. Okay, now we say, then I say that SLB measure is an equilibrium measure for some specific choice of F0. Okay, now there's a conjecture state the following due to Owen and Rel. He said that for topological mixing Anosov flow, maybe G. So for any and then for any let me just say there exists depending on G, depending on F bigger than 0, such that for any smooth function, you know that if you consider the correlation between these for GT, then the correlation decays. And the exponential speed. This is smaller than something determined AB, and also this e to the power minus t, and this alpha. So there's a lot of work related to this. I think the most general work, the most general statement. The most general statement is due to Toggle. We can show that so this is showing the following case. So we need to assume that first of all, we need to assume this ES and EU and that's C1. And also you need to make some assumption on the this equilibrium measure. Basically has doubling property. So under these assumptions, and he can prove this theorem. Okay, so I mean the result I want to present is to say that if we need to, maybe it's just some evidence to this conjecture. If we just want to prove this for a dense set of choice of G and F, then we don't need these assumptions. This is a theorem trying to work with Anosov. In fact, as we will see, if we just want to prove it for a dense set of this data, the proof is somewhat easy. So the statement is the following. If you consider a set of maybe this is generated by VG, generated this. Okay, so if you consider VG, the set of VG and also F, we put the right topology on it. We put the C-infinity topology on the first data. We put the Holder topology on the second data. Then we say that there is a dense set of FG such that, so this conjecture is true, such that we have exponential mixing for this data. So let me try to sketch.
So here, the M is the base manifold field is fixed.
Yeah.
And then the VG you choose VG such VG subset is then subset in such that it's topological mixing.
Yeah. Within yeah. Topological mixing under these assumptions. Yes. Thank you for the question.
And so it's just dense. You don't have like openness or other things.
What?
You have some, because you sometimes people want to show some generic thing like dense open set.
Yeah, so that is the problem. So I think we cannot show it is generic, right method. Sort of this is very soft, but it's very challenging to get open conditions that imply topological mixing. So we cannot do the usual Bayer argument to deduce the genericity of the mixing. So for now, we only have a dense set. That is what I understood. Okay. So anyway, I will try to convince you of this in the next maybe half an hour.
How about the two conditions over there? Are they true for a dense set?
What?
The two conditions you have on top. Are they true for a dense set of the data?
The two conditions here, ES, C1 and UF
Oh,
doubling.
okay. This is far from a dense set of condition. I don't quite understand the second condition. So I don't understand when it will fail. It does not fail for SRB measure because in that case the conditional measure to define this is like absolutely continuous, of course you have everything you want. And this, usually you don't have this. It's like usually you always have a held regularity, but it's very rare for these maps to have C1 regularity. So let me describe the proof. So we use the method of and then basically what he did is that he find the Markov partition. I mean, it's not he used a Markov partition to reduce this flow into a sort of a semi-flow. But let me describe without writing, just describe in words what is a Markov partition. So it means that there's a finite collection of local stable manifolds, and it looks like this through some point, and then there's some unstable manifold, stable manifolds through the same point, and then for each point on this U alpha, we form basically we form a union of stable manifolds, and then through this U. Okay, when this is a topological mixing, so say if you want to start from this point, unstable manifold, then this unstable manifold, like usually it does not lie on the surface, this topological surface. If for every point here, if you you take the unstable manifold, it lies on the surface, then you don't have topological mixing. So we call this thing alpha, and then it's like we have a finite fraction of this pi alpha, and then this thing together they form a Poincare section for the flow. So every point, if we flow forward and backward, it will always line on this point, and this gives us a Poincare return map for this thing, and let us call it as a sigma hat. Then what is important is that for a point here, let's take a point here and record one coordinate of this as x, so let's say this is b, the other coordinate is y, and let us write xy to denote the point here by taking the stable manifold for x and the whole center on stable manifold through y. Okay, so this is like this at a point that we denote by xy. Okay, so then what is important is the time. Is that we have this xy, and it will take this form. It will take be g. This is now x of x. So this is independent of y. Okay, so that is because we're taking unions of stable manifold. Okay, so then I'm going to fast forward.
How is the return time?
What?
How is the return time?
What?
How is the return time?
Yeah, how is the return time? Okay, return time.
So what's the dimension of M now?
What?
What's the dimension of M?
It's any dimension. So now I'm going to fast forward and omit many classical arguments to reduce the problem of proving this exponential mixing to a study of the operator defined like this, so-called twisted transfer operator, LAB. So,
A question. Dolgopiat, in Dolgopiat, the paper about Dolgopiat, he had a condition called non-uniform uniform non-integrability.
yes.
So is it equivalent with doubling property, or does it imply?
No, it's not it has a little to do with the doubling property, I guess. Doubling property, okay, maybe I didn't explain. Yeah, maybe you're right. So there's a measure, mu f, right? And the measure, you push down the measure by the flow, you get the invariant measure on this union of this. So let's call this measure as maybe tilde on this, or maybe tilde like this. A measure on this. And in fact, we can do another projection, get a measure on U.
Yes.
And the doubling property says that this thing, you take a small ball, and then it's comparable to a ball of a half size. So this is a doubling property. Okay, but I don't know when this is true, when this is not true. Okay, so the operator defined as follow. So first of all, operator acts on functions of this, or maybe let me use another. This. Then you write as follows. Take a u here. Maybe let me take phi here. U. And then it is defined by u. So as I said, you can reduce the dynamic here. You get a non-invertible dynamic on U. So you have a non-invertible dynamic on U, which is the factor of this invertible dynamic on this. Then you will take this form. This is some function. Let me write it. Some function constructed by derived from f. The construction is complicated, so I don't want to go into detail because in fact I don't have to remember how this is constructed. Then maybe let me write v. And you have a phi v here. And v is in the preimage of u. Okay. So it comes down to show the following estimates. All of these are very, very classical. I mean, exist in 1980 something. U. This is U. You want this to be smaller than B to some minus some power beta of the some this. You want this for, or let me write like this. This is A, this is B, and you want this to hold in this region. In this region. So when the absolute value of A is small and when the absolute value of B is big. So once we have this, then we can show exponential mixing.
I think it's norm for phi, not for u.
What? Oh, okay.
Fine.
This is fine. This is the semi-norm. It's not so important. So now we want to take another point of view on this. Looking at the sort of this weak statements on density that we have. So we want to consider this, the left-hand side, as a functional space of
Not homogeneous, the equation here.
what?
Not homogeneous in phi.
Okay, yeah. So Square root on the left.
Square root on the left, maybe.
Yeah. So we look at the left-hand side as a function. And then, oh, sorry, there's an important missing. There's an n. We want this to hold for n bigger than some bigger than this for some c independent of the ab. Okay, so what we are going to do is we consider this as a functional. I mean, how does this thing depends on this vg? First of all, we can say something simple. So, like, we can just compute this and then by some coefficients. So in the end, it comes down to show the following thing. Let me write directly the same. Like we want to show for any phi such that phi is real value. And also need this. Maybe for some another b. Let's say b0. Then also wants one to be smaller than equal to 1. And then we want to see that just a set of
So what is gamma? So what is phi gamma?
phi gamma. This gamma is a whole exponent and phi gamma is a whole seminole.
What is on the left? What is phi on the left? Evaluated on a point? What is it? No, downstairs. What is this here?
So this is a real value function. I said that we can reduce the real value. Real value. So
You want for any x?
any
u?
Yes.
For any u. Okay.
Okay, so let's even make.
Still have a question, like, here if you change VG, do you also have the same Markov partition?
Yeah. No, it's like you need to change VG by do time change. Right? If you don't do time change, you will move. But if you do time change, you have like a continuation you can study. That's the main point of the argument. So what are the following? So let me just wave some hand. Let's say for a typical choice of two branches. Typical choices of two inverse branches. One inverse branch, let's say V1, let me say that's V1, V2, inverse branches. By typical, we mean that except O B minus C, these exceptional cases. For the rest of the choice of Vx, we want to consider the following, want to look at the following functional. T2u so we want to say this smaller than the integral. Let me state the quantifier is the following. The quantifier is that for typical choices of two these, then for any phi, satisfying this condition, we have this
It's B minus C.
b minus where? Okay, b minus some exponent, some maybe. Okay, so this I want to say, so for you have choices of v1, v2 you can make. There are many choices. And I say that for typical choice, meaning that the exceptional pairs is at most in proportion. Yeah, so I have this much. And b to the minus c. Exceptionals.
So the complement of the set of inverse branches you're considering has measure B minus C
Yeah.
for the uniform measure
Yeah.
of the set of inverse branches.
Yeah, but in that case, you can ignore this because it will contribute not much. This transfer operator, they have an operator no 1, 2 or something, at most 1. Okay, so now we are going to consider this as a functional, and we are going to perturb G within a nice family. Okay, so we perturb G in a nice family. So we do the following. We want to consider the space of all the time channels of G. So this gives you, let's say, C. We're trying to show C infinity density, right? That is about the CR density first. So maybe let us consider all the smooth tangent of this is the space of. Let me write it like this to start. Time changes of G. Right? You just take a function and you do the time change. And in fact, when we want to show density, of course, we can only take a small ball of this, close to 0. And then we want to show that for typical time change, we have this. And then we can do some Borel-Contali argument too. So how do you do this? So in fact, the only thing we need to do is to see that because we have a lot of independent way to perturb these two things sort of independently. Then it's like we have a lot of random variables that are up, like we can perturb independently. And when they sum up, then on average they will have a lot of cancellation. And the cancellation is very strong, so we'll have no problem to do this a lot of times, as long as the times is a polynomial of B.
Sorry, is the property of the exponential decay of the correlations sensitive to time changes?
Yeah.
So there are examples where you do a time change and then you make it.
No, you just start from constant function. So constant root function, it is not exponential mixing. And do time change, it becomes a. You can do constant function.
Constant function is not mixing at all.
Because, right. I'm thinking in the case where you don't have this sort of suspension alternative. I mean, A is split into 2, right?
It has the same structure of suspension.
But if you are in the other case, in the other alternative.
This business with mixing, it is always very sensitive to time change. You can have something weakly mixing, you do a time change, it becomes mixing. There are a lot of cases. And then we are making use of this to do exponential mixing. I'll ignore some details. It has a statement about how to choose these two pairs. Basically, you want to see. So it's like one inverse branch corresponds to one unstable manifold. No, one location here. Another corresponds to another. And then the difference here corresponds to when you consider you start from this place to go from this place, or you go from this place to this. Then there's a difference in between, right? And we want to be able to perturb and control very precisely or approximately how this difference moves. So in the end, the type of perturbation we will make is really what people expect. So it's like you have this unstable manifold, it will be higher dimension, it will be many dimension. But we will decompose it into maybe small balls, many small balls. Now each of these small balls will have size b to the power minus, let's say, some beta 1. Here beta 1 is very small. And then so maybe this is just one piece here, but then maybe this corresponds to one inverse branch, V1. And there's another inverse branch corresponding to this. Yeah, then we don't do anything. Don't do anything. So we're going to let's say, so this is the flow direction, and this is the flow. So we are going to make some perturbation here, so that when you go along with the flow, the perturbation is going to change what happens here, but it does not change immediately what happens along this line. So this is I don't know how to draw three-dimensional picture on two-dimensional board, but in fact, this is basically looks like this. And on this thing, we don't see it. So as the flow goes through here, things change. But when it goes here, nothing changes. And also when it goes continue to go away, you don't run into the part you do perturbation immediately. This tells you that the stable manifold here, it doesn't move much. And also the same thing holds for this part. So in the end, the only difference this perturbation make is on the unstable part, how this change. And that will contribute to term here. So then let me just try to discuss some difficulties and how we solve it. I mean, one clear difficulty is that this is an infinite dimensional space. And for all of this bigger and bigger B, you need to make small and small perturbation, and thirdly, you have infinite many parameters. And you have to group this information for all of these parameters together to say something. And that is done by picking good measure on the set of this on this set of time change. So
in this process, the potential F you don't change.
yeah, that is a good question. So potential F does change, but it changes a little bit. Does not change a lot. So once you can prove by doing small tangent you can do things, then it's like you're moving F and also potential simultaneous to some point. Like you're moving these two things together along the time chain, right? And then so in the end we are going to consider the following thing. Let me directly here. So this thing is very much approximated by some constants times e to the power I phi, and the t here, the vector, tell us how to perturb by time change. And also there's x, I'm using u and the v1 vt. Okay, and then this test function here. Okay, so and plus some terms that is not important, plus some C. And then this is what. So we'll do a high dimensional perturbation. It's like for each of these box, we put a bound function. and we have a lot of bound functions. Good bound functions as well. So each bound function, so we have this, at first we have g, we do time change by 1 plus t, and this is a function. So what is this function? So this is t1 plus t1 phi 1. Okay, it depends only on x, right? On the point on the manifold. T some number, let's say k, 5k. Okay, so these are supported in some of this box. Maybe this is supported in phi 1 through phi 2. Okay, so it is like we can do independent perturbations. Okay, so each of these is supported. Let's say this so you can think of this, some j supported in some vj, which is contained in some ball xj of radius b to the power minus beta 1. Then remember beta 1 is very small compared to the, and the beta 1 is small, so you can do this so that the C0 norm of maybe let's make the B inverse to be coupled with the B. So in the end you can say the C0 norm of this each phi j is 1. It's like you have this region is 1, on that region is 0. But at the same time, maybe this CR norm is smaller than 1 as well. Okay, but if we do this, then there will be some problem because the idea is that you have this space of time change, and you want to choose some good measure on this. And in fact, for any measure we choose, so some phi we choose on this, it is not going to be absolutely continuous to itself by translation. But there's a construction by Masato. We can show that if you translate by some vector which is much smoother, you can have absolute continuity. So in fact, if you do this, maybe some functions phi 2 phi plus then it's like if phi is c plus 100, or let me write this r, for some r much bigger than r, then if you push forward this measure by translation, then it will be absolutely continuous to itself. And Radon-Nicotin derivative is e to the power O.
Sorry, but how can the function psi j be supported in the small ball and have like C0 norm equal to 1 and C0 norm less than 1?
No, because the size of the ball is beta 1. And then this r is like r times beta 1 is small. We choose this to be very small. So it's like a ball is actually big. No, I mean, beta 1 is something very small.
Yes, but beta b to the minus beta 1 is small. I mean, still small. When b goes to infinity, the ball has...
sorry. Yeah, I forgot to write something. Yeah. It will be
b to some power.
There's a b inverse here.
So psi j c0 is not equal to 1.
Yeah, it's like this. You want this. It's not individuals. Sorry. It's like this is used to translate, to do the translation. There's a b inverse here. Coming from.
And the question remains.
So what is the support of psi j then?
What?
What is the
So
support?
all the psi j is still like this of this size. Let me there's an interval for some j1, j2. They are spaced by maybe something bigger than b to the power this, and then you take a ball here, and then you can make a bump function so that maybe the CR norm will be b to the power beta 1 r. And then because you have a minus
Okay.
minus 1, yeah.
So it's psi. Yeah, the CR norm is the CR norm of psi, not of psi j.
Because this, eventually we are going to use this to translate the flow.
Okay.
Okay, so once we have this, I don't have enough time. Okay, so I will try to explain how the computation goes. The main point is that we are going to consider and we say that modulo some small error of this size, we can come down to control this sum. Control, let me write what is AJ. AJ is the area of VJ. And then in this place, we can put I plus I T as the and then we want to minimize, we want to like make this kind of small to see a lot of cancellation if we have a lot of independent controls. So we're doing this. So how to do this? So we're going to consider this integral of g minus, let me write directly what I have here. Maybe A inverse. This is B2. So A is the square root, is the square of this, where this J takes a finite connection of this. They're not going to be everything. But if we would take like a lot of them, of some b to the power like j, of b to the power something positive or very small, we're going to consider this thing. Then it's like when we have a good choice of v1, v2, these two inverse branches, then it's like you know the determinant of this thing is determinant from T to T uj v1, v2. The determinant of this is bounded from above and from below. So this, we see that this is a positive, that everything is positive, so you can just put out the determinant to simplify this. It becomes times something, basically this. And then we can compute this. So computation, because you can put out this, you can do this. And this, you can do tight expansion and plus 0 plus the second order term, which is the p to the beta. So in the end, it's bounded by exponent to the power 5 and k. So what is beta 5? So I have very little amount of time, so I will not be able to say more. But maybe there's a question, open question session this evening.
Yes.
So basically, if you pick a subset of this J, so that each of these box, V1, Vj, the size of them are not very different. It's like you want the following relation. You want to know that and also just this. So once you have this, then let us consider. So first of all, this happens if let's say aj and ai, you take the log of, so it's like they are kind of close to 1. Close to 1, then you have this. There will be something positive in between. Then let us compute this thing under this assumption. So if we consider the set of T so that this is actually big. All of these, they are bigger than b minus beta 6, and normalized by the sum. Then you can just use Markov inequality to see that I use it to bound y. So y is bounded by inverse this thing times this is 2 and minus this is the thing to add in the beginning, and the rest is the union of them be beta 6. Okay, so this is smaller than but then under this condition, you know that in fact this Vj is actually bigger than B2 minus 5. Just look at the last thing. And then you can continue to compute, and this is bounded by element of C. We just use to 6 here, and cancellation 1. Then the whole thing becomes beta 6, and then you consider what is A inverse. No. So A will be, in the end, the computation tells you this. So it's like when you do this, when you consider this thing, then the set of T, for which this is a little bit big, is very, very small. I mean, it'll be, if you do this thing, polynomial power of T of B times, you will still be left with a full measure. And this is the main argument. And we have two. So the picture is like we have a ball, we have time change here. For each g, we use perturbation to see that along each this finite dimensional set of perturbation, we have the bad parameter will have very small measure. But then the same set of perturbation can be done not only for G, it can be used for everything close to G. So it's like you can do some forbidden argument to say that in the end, with respect to that measure, this measure here on this space, with respect to this measure, most of the parameters, they will give you a lot of cancellation, and you group them together, and you see decay. So that is the proof.
Questions?
So you have a picture on the top board of a Markov partition. So your picture is for a three-dimensional Anosov flow. Yeah. And in that case, the unstable manifolds will be nice one-dimensional intervals. If you're in a higher dimension, then these unstable sets are going to be very, very complicated. Yeah, I wondered how you got the cancellations on your integrals, if these sets are very...
the boundary have a zero measure, right? The boundary have a zero measure with respect to the thing. And you just modular, you can take a small interval, a small neighborhood of this, a color of this, and then all of those is going to contribute something. If you don't have cancellation, then you just use the trivial bound, the C0 bound, and then to use the measure.
These sets are not going to be very connected, they're going to be very disconnected in general. Is that? The sets U, I can't read the subscript, maybe alpha.
Yeah. Like U is not connected, it's like a finite many connected.
It could be infinitely many. I don't see why it's finitely many.
Like there are infinitely many?
I don't see why it's finite.
The Markov rectangles?
Yeah.
They are infinity.
Well, an individual rectangle in higher dimensions can be very complicated.
Let's say, so in Dogopia's case, he has finite many. He also studied higher dimension, right? He has.
I'm not a great believer in Dogopia in high dimensions. Some people are.
So you say that in higher dimension, one cannot construct the finite many partitions.
Not that I'm aware of. If you know a construction, I'm happy to hear it.
But the point is that I guess this is under the assumption that there's a finite Markov partition for that. Okay. But let's say, so all of these arguments you only need to perturb for one thing. You see, the only place where you have infinitely many things is to take branches. But the only thing you want to avoid the complicated thing for branches is that you don't want one branch, one stable manifold to get very close to itself very quickly. But there are only very few unstable manifold that is going to get itself very quickly because by this Anosov lemma, that is going to give you a periodic orbit. There are only like growing many periodic orbits. So so for instance, the condition for choosing these inverse branches, I think the inverse branch is the only place we use some will be linked to the finiteness of the condition, or the others like our neighborhood of this. We want to say that under log b from c times, it does not get close to itself. As long as this c is much smaller than beta, then it's okay. Right? Because once you have these, then when you pull back, it will give you some periodic orbit, and there will be, so basically this thing will be close to a periodic orbit of length this by Anosov closing lemma, but you have e to the power entropy times length many periodic orbit. Then it just corresponds to small measure as long as the beta is bigger than c a lot. Then after removing this, each time we fix two branch outside of the when these two branches fixed, then it's like we have to do a parameter exclusion. I mean, the only thing could be a problem is like there are, we have to do this much, I mean, this much parameter exclusion to get rid of all of those small branches you consider. Well, I hope that they won't happen. As long as this, you said there's like infinite many branches, as long as there's a little bit of decay, then you don't need to consider all those ones. You just use trivial.
So I have one question related to your theorem. So you seem to be claiming density for the pairs, right? You have to move the vector field and the potential. Suppose you're interested just in the SRB measure and you would like to prove something.
Then like for SRB measure, this time change will map one SRB measure to
another.
So for SRB measure, the statement is slightly nicer, and we'll say that for a dense set of Anosov flow, you have exponential decay with respect to SRB measure.
Right, and then if you were to take another equilibrium state for which you do not have this sort of nice property with time changes.
We don't know.
And the general conjecture is that if you have something that is topologically mixing, it should be.
Conjecture, I guess, is to go from, so topological mixing is like at the O1 level, you have non-integrability. You want to somehow propagate it to all.
So if you're in the non-suspension case, then all time changes should be mixing. So exponentially mixing. So this, you can, if you have an Anosov flows, you have the case of the suspension. I mean, you fail to be topologically mixing if the flow is topologically closer to a suspension, right? So if you have, in the case like the geodesic flow, that will never happen. So in that case, you would expect all the time changes to be mixing with rapid decay, right? Okay, so let me rephrase the question. You take just the geodesic flow and you make any time change in the geodesic flow. You would expect that to be exponentially decaying for the correlations, right? All time changes.
It is always topological mixing. You say in the context you consider, it's always topological mixing.
Yeah.
Then the conjecture will suggest that you always have exponential mixing, but
okay. So I think it's any other questions? Okay, what is